Today's webinar will be on generative design technology with 3D printing based on Autodesk and Markforged technology. And I'll just go through the agenda. So the agenda today will be on what is generative design, who uses the software. We'll go through some case studies, and then a generative design software workflow to 3D printing. And we'll go through some composite and metal industrial 3D printing technologies from Markforged. So generative design software, this is some of the screen grabs from the software. So what is it? It's the process of taking a 3D CAD model, then applying parameters to that model, and then exploring what the outcomes are based on those parameters of that study to optimize the part. So if you look at why we do it, material reduction. A reduction in weight is important for product designers and manufacturers. There's a reduction in cost also if you can reduce the weight and the material. You're more competitive, or you're more profitable. In terms of innovation, there are new alternatives you can explore and new technologies. You can now leverage on new technologies with these generative design tools. So if you look at these 4 points that we covered, it's all about growth. If you're more competitive, you're more profitable, and you can explore new alternatives and technologies, companies grow. So who generative designs? Companies like Airbus, Under Armour, Stanley Black & Decker, BMW, and General Motors. So if we go through some case studies on generative design, you can look at Stanley Black & Decker as an example. So Stanley Black & Decker have a pistol grip crimper. It's used by utility workers where they crimp wires during repair and maintenance of overhead power lines. So yeah, as I said, the tool is used overhead, and with the overall weight being 7 kilos, the goal was to make the whole assembly lighter. So what they focused on was the C-head tool, which is 2.4 kilos of that 7 kilos. So what they did, they used generative design software to come up with new variations based on a set criteria. And based on that, they were able to reduce the weight of the C-head tool by 60%, from 2.4 kilos to 0.95 or 950 grams. In terms of a second case study that is used for generative design, that's GM in the electrical vehicles division. So, I mean, it's not just in the electrical vehicles, but in all vehicles, there's a car seat bracket assembly. So the EV division were looking at ways to reduce the vehicle weight and extend mileage of the car. The car seat bracket assembly secures seatbelt fasteners to seats and seats to floors. And it's an 8-part assembly that's welded together. So with those 8 pieces, the goal is not to only reduce the weight, but also consolidate these parts as well, as much as they could. So they used generative design software from Autodesk to, yet again, explore different variations based on a set criteria. And here's what they came up with using the generative design software. So the car seat bracket assembly is now a single part. So from 8 to 1 is pretty massive. So also it reduced the weight by 40%. And it was 20% stronger than the previous design as well. So a lot of benefits there, but the ancillary benefits of using generative design software was that it also reduced their supply chain costs. That they don't have to go to market and get 8 pieces produced and sent back, and then the assembly costs also. So there are some flow-on benefits that were realized, and now GM are looking at what other parts can they use generative design to reduce the overall weight of their parts. So RedStack, being an Autodesk partner and also a Markforged partner, create an example of a Clevis, which is used in many applications in industrial and commercial products, in hydraulics and pneumatics. So we use the Clevis and try to optimize that. So when we applied the material stainless steel, it was 1.5 kilos, and the rough dimensions of this Clevis was 120 by 72 by 87 mil. So it's typically welded from 3 pieces. Then the holes are machined into it. In terms of setting up the study in the design software, we set up a generative design study. Sorry, we're technical difficulty, just bear with me. So we've set up a generative design study, and so what you do in the software, you define what can or cannot be changed. So in this example, the green rods show the areas where we need space so we can get to the bolts and the center pin. So when we ran the study, the software shows thumbnails of every possible alternative. In this study, it showed 35 different alternatives that we could choose that met the criteria. There's also a chart where you can review designs based on mass versus the factor of safety. And once the design is chosen, you can clean up areas before 3D printing them. So you can use that in your CAD software or an STL design software like Mesh Mixer. In this example, we use, I think, a combination of Mesh Mixer and Fusion 360 to clean up the final part. So this is what the 3D print looked like. When you apply stainless steel as the material, there's also a 60% weight saving compared to the original design. And the factor of safety is still 3. So it's quite acceptable. So to be able to design the part using current 2D and 3D CAD tools would either be very difficult or near impossible to produce such a design, especially in 2D. And then on top of that, to manually explore and validate so many different alternatives, like 35, is impractical for an engineer. So these are the benefits also of using generative design software to do the calculations and thinking for you. And then taking that optimal design and putting more effort into it and refining it before manufacture. So what kind of software does generative design? So Fusion 360 is one application. The Product Design and Manufacturing Collection has both Fusion 360 and Inventor Professional. And Inventor Professional also has a more simplified version than what's in Fusion 360, where you can set up a design study and it'll only give you one alternative. It'll optimize the design, and then you can refine it further. So let's look at what the generative design software looks like in Fusion 360. I'm just going to play a video. Hopefully it plays quite smoothly. So in this example, we're setting up a study here. After importing the STL file, there's 5 things you need to do. You need to define the constraints and loads. You've got to specify the design requirements, meaning, what are the objectives, the type of manufacturing and materials. So if you look at applying constraints, you can apply a fixed constraint to a face and lock it down, or a frictionless constraint, which will prevent the face from moving or deforming in the normal direction of the face. You can apply a load or loads. You can apply a pressure, force, or moment of load if you want to simulate the effects of a torque or bending of your model. Now, this is where you specify design requirements as well. So With the objectives, there's two options as well. Look, I think I'll just wait for the software to catch up here. So yeah, as I was saying, you can apply pressure, force, or moment load if you want to simulate effects of a torque or bending the model. So this is where you specify design requirements. So with objectives, there's two options. Do you want to minimize mass or maximize stiffness while maintaining a factor of safety? If it's stiffness, you would need to specify the mass target. So you really want to make sure your parts that you're designing meet the factor of safety, and when the final design is optimized, you know what the targets are, and you know, to get a good outcome, I suppose. So when it comes to manufacturing, it refers to additive manufacturing. How much overhang do you want? With also a reference to supports, and what is the minimum thickness as well. So in here, we're putting the overhang angle of 50 degrees, and we want a minimum thickness of 0.05 in the software. This will give us an acceptable outcome. So materials is pretty self-explanatory. You choose what materials you want to use. So once you choose what kind of materials, it gives you some, you know, specifications. You can create materials as well. So if you're using, you know, composites or some special filaments or things like that when 3D printing. So I guess now all we need to do is generate a study. So with Autodesk Generative Design platform, you need 25 cloud credits to run a study. So each study is about $40. So the computer comes back with a bunch of outcomes. So on the left, you have a slider bar with ranges, with the sort of metrics like volume, mass, displacement, and stress. On the right, you have thumbnails with additional information. The video doesn't show it, but there's pretty insightful comparison tools to compare one outcome over the other as well. So that's a brief overview of the generative design tools with Autodesk. So I'm just going to get into high-speed desktop and industrial 3D printers from Markforged. So Markforged is all about unlocking the next 10x innovation design and manufacturing. And what they mean by 10x is they refer to comparing their 3D printing metal technology compared to others. You know, 10 times safer, 10 times lower cost, and 10 times faster. So Markforged have an industrial 3D printing platform where they supply cloud-based software, which can be also made on supplied on premise, a full range of industrial 3D printers from desktop as to industrial range, and purpose-built materials for strong parts, not only in composite, plastic, and metal. So what can they be used for? Functional prototypes, end-of-use tooling and fixtures, and production metal parts. So if you look at their range of printers, you have the desktop range, and that starts at the Onyx 1. Onyx 1 printing in a material called Onyx Only, which is nylon with chopped carbon fiber. It's around 40% stiffer than ABS. It prints in 100 micron, and the build size is 320, 132 by 154 on the whole desktop range. If we go up to the Onyx Pro, it will print in Onyx and then continuously reinforce that with fiberglass. Fiberglass has an MPa of around about 240, which is close to or above that of mild steel. So you could potentially print in Onyx with fiberglass, create a prototype, and test it with loads that would give you a similar performance of that of mild steel without having to create molds, dies, or CNC a mild steel part. And then if you move up to the Mark II, you can choose between Onyx or nylon as a base material, and then continuously reinforce that with fiberglass, Kevlar, high strength, high temp fiberglass, which is stronger than 6061 aluminium, and carbon fiber. If we move on to the industrial range, very similar concept. The X3 does Onyx, the X5 does Onyx with fiberglass, the X7 does all materials. You can also print in Onyx and nylon rather than a choice of one or the other. The build size is larger. We go from go to 330 to 270 by 200. It'll print down to 50 micron. It'll do 100 micron. I think it does also 200 micron. But the biggest thing that the industrial has over the desktop is quality control systems. It's got lasers to flatten the bed, offset. So, and then when it does the first couple of prints, it also runs a laser check to make sure that the first couple of layers are level, and then it compensates for that. The X7 goes one step further, where it'll do a laser scan midway through the print, where you can then bring it into the software, overlay that with a 3D model, and check it to make sure that it is accurate. So when it comes to a workhorse that prints all day, every day, and quality control with repeatability, you would look at the industrial range as opposed to the desktop. So if we look at the whole portfolio of printers, on the left you have the desktop range, on the right you have industrial, X3, X5, X7. To the far right we have the Metal X, which we'll get into a bit later. Currently it does 17.4 pH stainless steel and H13 tool steel. Later in the year it'll be coming out with titanium, grade 5 titanium, Inconel, copper, A2 and D2 tool steel, and some other materials as well. So you get cloud software, IGA software with the printers free of charge, whether you buy 1 or 1 million printers. You can also get local storage free of charge. If you are a defense customer or have very IP sensitive data that you don't want in the cloud for whatever reason, you can purchase on-premise software and have it off the grid, I suppose. So what sets Markforged apart from other 3D printing technology is the revolutionary surface. By optimizing the hardware, software, materials together, they set a new bar. And it's highly repeatable extrusion, which means it is a great surface finish and the key to dimensional accuracy in parts that fit perfectly in your application. So these ball joints are printed in 2 separate parts on 2 separate machines, and they just screw together. Since it's 17.4 on 17.4, they put a dab lapping compound to prevent galling. So anyone can print large threads, but only Markforged has the accuracy to print small, high tolerance threads, I think down to M3. So if you ever want a sample part, we're having an event later in October, and we're having a roadshow in Brisbane and around Australia. So you can see these metal parts in action, or contact us to set up a meeting and see these parts. So Markforged have a global fleet of installed printers all around the world. There are customers in many different verticals. And when it comes to outsourcing parts for CNC, if you did it in-house with 3D printing with Markforged, you'd save a lot more money. This data was put together from typical outsourcing costs versus people who were printing on the IGA software. So if we look at chopped carbon reinforcement, you'll see on the left there, that the Onyx material is a lot stronger than ABS or nylon. And on the right, when we start continuously reinforcing that fiber, the carbon fiber and high strength, high temp fiberglass is much, much stronger than aluminium. And the fiberglass, as I said, was up around the 240 range, and it just blows away what you can do in ABS printing. As I was saying, with the X7, it's the only Markforged, only 3D printer that has quality control systems for under $1 million. It's got a full sensor suite, including motor encoders and a calibration laser. So it's so accurate it can compensate for single-digit changes in room temperature. And as I said, the X7 features laser inspection that scans parts mid-print to ensure dimensional accuracy. And that's really for the most critical tolerances. So if we get to the metal X and the technical specifications, sometimes you just need metal. So when your application requires isotropic strength, high temperature resistant, when you think about injection molds and the harder surfaces, you want to print in metal. What's great about printing in metal, it's important because your prototype and production solutions should use the exact same technology. In many cases, people use one technology for a prototype and a different technology for the end process, end part, sorry. So every process requires different part design, be it CNC machining, injection molding, casting, or different 3D printing solutions. For example, in the Atom process, which is Markforged's metal printing process, you can produce parts with closed cell infill. You can't do this with any other powder-based 3D metal printing solution. So this brake lever here has a 50% triangular infill throughout the part, making it lighter. So that's important for a motorcycle. So once you validate the part for your application, you don't want to change the structural design and use a different method. And that's what's so important or so great about Markforged metal printing. So they designed the Atom process based off high volume production technique called metal injection molding, or sometimes called MIM for short. So iPhone parts, hip inserts, and FAA flight certified hardware are made with MIM every day. So at Markforged, they print their own demo parts, which gets sent to partners like us and customers. They make about 11,000 parts per month on a fleet of 30 printers managed by one operator who's not a trained engineer. So they'd be mass producing these ball joints for sample parts. Each of these ball joints takes about half an hour to print across 2 printers and costs around $1.95 US to print. So ATOM stands for Atomic Diffusion Additive Manufacturing, and at the intersection of 3D printing and metal injection molding, ATOM is the all-new way to build metal parts. There's a 4-step process. It starts with your CAD design. You design the part you want and you upload the STL to the Markforged software. You then print the part out of metal powder, which is bound in a plastic layer at a time. And then parts go through a washing step and then are sintered into their final metal form, where it turns out up to 99.7 dense, and it's ready for use. So if you look at an end-to-end metal solution from Markforged, it's the Metal X printer, it's the wash, and the sinter. You can choose from a sinter 1 or a sinter 2. Or you can go to high volume mass production using a MIM. So metal injection molded furnaces are designed to keep up the speed and volume of injection molding. They handle incredible volume and are used for aerospace, medical, and automotive applications. So if you look at the Metal X technical specification, as I said, the process is Atom. The build volume is 300 by 220 by 180. The machine size, it's about 75 kilos. It's got a heated chamber. The print bed's heated. It's got a vacuum sealed print sheet and auto bed leveling. It's got 2 nozzles, one for the metal, one for ceramic. So it prints a metal bed and then prints the part on top of that. And in between those 2 sections are ceramic. Printed. It's printed in ceramic and then releases off once it's sintered. So it'll get down to 50 micron as well. But the maximum part size is about 10 kilos, even though the bed size or the build volume is larger. 250 by 183 by 150 is probably about the largest that you can print out of the Metal X. So the great thing about Markforged technology, you can seamlessly scale from prototype from production. Because the software is cloud fleet management, you can hit print on the software and go to 1 or 100 printers or more.